Hello, in this video I'm going to do a final exam review for CE241 Fundamentals of Computer Logic, and this will be an open book, open notes exam, and it will be 90 minutes, which is 1 hour and 30 minutes, and there will be a few problems, and I'm going to do a quick review pretty soon, and there will not be any simulation problems, and also there will not be any Verilog problems. Okay, I just changed my idea because I don't think you guys have been trained intensively in these topics, so probably it will be a big issue for some of you guys, and it won't be that far. All right. So now let's take a look at what's gonna be covered on the exam. First, you have to be able to do the number system conversions really well. Okay, this is the first module, what's covering the first module. And that's super important stuff you need to know. Okay, number system conversions, including binary, decimal, octal, hex, and an arbitrary number system. I don't know, for example, 3-based, 4-based, 7-based, 6-based. And you have to be able to know how to convert the numbers back and forth, not just this, okay? It's going to be this, like this, any of them. Okay, all of them, and then going backwards. I'll make it a little bit more difficult compared to the midterm exam for this specific problem because I'm assuming you guys are getting better and better in these similar topics, so I will have a higher expectation. Number two will be all these operations, addition in binaries, so addition, subtraction, multiplication. So definitely you are probably are thinking, oh, these problems are just repeating the midterm, and we are still getting 90 minutes. How that is possible, right? So I will not just list all these the same number of problems, the same type of problems compared to the midterm, but I will pick up some of the ones most of you didn't make it right. So I want to just test you again in the final exam. See if you really did a review on that. Multiplication, division in binary. Okay. Number 3, Boolean algebra, of course, and Boolean algebra and the theorems. Which means if I give you a logic expression, can you prove it? Okay, use all these logic theorems, whatever. you have learned. Right? It won't be that difficult. So the most significant one will be, since like A or B, C equals to what, right? A or B, A or C. Or, how to prove this. Or, sorry, how to prove this, right? Problems similar to these ones. Probably will see this on the final exam. And then we move to K-map, right? K-map, SOP, POS, things like that. And static hazard. And timing diagram. And what else? So this involves a time delay, right? So you may see something a little bit more difficult than what you saw in your homework assignments, okay? But it's a similar principle. You're just using the same methods to solve another problem, which is a little bit different. Maybe just more gates, right? Just you will. It's so this kind of problem itself is not that difficult. You just need to understand the theory behind it. If I add more gates and make the circuit a little bit more complicated, you just just do it. That's K-map, SOP, static hazards, 1 or 0 hazards, and timing diagram. And what else? The combinational logic circuits, right? Full adder, half adder, and mux, and decoder. Pay special attention to decoder. So this is in lecture 17, I guess. And I'm gonna give you an example after I write down all these parts. Can possibly will show up on the final exam. So I'm gonna come back to here later. Number 6, sequential logic, right? SR latch, SR flip flop, JK flip flop, JK master slave flip flop, T flip flop, D flip flop, and yeah, all these different types of flip flops. And also you need to know the counter, how to build a counter, and shift register. Pay attention to this as well, and also counter. So shift register and counter are being covered in the lecture of 22. And also switch debouncing. We didn't have a homework assignments for these ones. Probably only this one do we have? Maybe not. I forgot. So anyway, watch the lecture and look at the example I showed you in the lecture and try to do it ourselves, try to learn it. And switch debouncing, use NOR. Do you know if I'm asking you to use the NOR gates to build a switch debouncing circuit, can you do that? Or use NAND gate to build it? Either way, they should behave pretty similar. You need to know how to do it. Okay, make sure you do it. So there's no surprise. It's open book, open notes. So I mean, you need to understand it first because you don't want to just rely on during the 90 minutes to to look for all these references or solutions online or from the videos, it's gonna running out. You are going to running out of time. So definitely do it before the exam. Okay. So that's the sequential circuits, and be careful about another thing which we cover in module 5, which is a milli and more state machine. So you need to know, if I give you a state diagram, can you convert it to a sequential circuit? This is T, right? So sequential circuit. Or can you convert it backwards? Okay, this is required. You need to know that. And all right, so that's pretty much all these stuff possibly will be covered and will show up on the final exam. I hope if you look at all these things, you can see that actually in this very short 5 weeks, you have learned a lot. And I hope you have learned a lot. Let's look at one example of the decoder. So decoder can be, you can design all kinds of output patterns. In the lecture, what we covered is, if this is a 2 to 4 decoder, you have 2 inputs and 4 outputs, right? So we are talking about the output pattern to be something like this. Right? So we just have one to be turned on at one time. All right? So all the rest of them are zeros. But it's not necessary to be zeros. This is just one type of output pattern. So the purpose of this decoder is like, whenever you have one type of input, you're just turning on one pin, one output pin here. So you only have one LED being turned on, right? But why? You can design a decoder to have any types of patterns, but depends on the application. So the number of patterns equals to what? Equals to the possible number of what? Input combinations. Think about if this is right, okay? So this is one output pattern, right? So let's look at y0 is 1, y1 is 0, y2 is 0, y2 is 0. So this is one output pattern, and you need a one input. It's like a password. It's like a code, right? You need this code to represent this thing. So the system, whenever the system receives that code, it's gonna output this pattern. It has to be 1 versus 1, right? 1 by 1. You cannot, use one input, one type of input have different types of output. It's not making sense. The decoder, right? You have a code, it's decoded, and you get a pattern of output. So this is one. If you have 4 patterns, right? 1, 2, 3, 4, which means you need 4 types of inputs or code to represent that, okay? Or to ask the decoder to do that pattern, to make that pattern happen. So in that case, if I'm telling you I have three patterns, right? 3 patterns. How many bits do I need for the input? It is still 2 bits. Why? Because only 2 bits can give you 3 outputs, 3 different types of outputs. So the maximum number of outputs this guy can handle will be 4. 1, 2, 3, 4. The thing is, one bit can only do two, right? But you have three different patterns, you still need two bits. You're going to waste probably the last one, which is just not using that. Doesn't matter. So what if you have 6 patterns? You need 3 bits. Why? Because 3 bits will give you 8 different types of patterns, right? But 6, 8, you're just wasting 2 of the different of the two inputs, right? What about 9? You have to use 4 bits to be able to decode 9 different outputs. So now you understand, you can design an arbitrary decoder with different patterns. So there are so many different applications. So the one I introduced in the lecture is a traffic light controller. You can see how I solve that problem using a customized decoder to make that work, right? So there's another pretty important application which is called 7-segment display. You must have seen this somewhere in the real life. So this is a 1-digit 7-segment display. So every bar here is LED. It's just a bar shape. So every bar is LED and it's being controlled by one of the pins. So if you turn it on, give a logic 1, it's going to turn on the LED. So you can have, you see how many bars you have. 1, 2, 3, 4, 5, 6, 7. So 7 bars. That's why it's called 7-segment display. Okay. And so you can control every individual LED pin to control every individual LED to turn it on, turn it off. So you can imagine that. So these are all these 7 segments. If I want to display a number 2, so I just turn on these ones. If I want to show a 0, so I just turn on these ones. If I want to show a 3, I'm going to do this. All right. So it just, you can define the voltage levels for each pin in order to show a different digit for this little display module. So we can use a decoder to do that. The reason we want to use a decoder is if we do not use a decoder, we have to control every individual one. Use an individual wire. So for example, for a 7-segment display, you must use 7 different wires. Give this wire a 5 volts, give that wire a ground, give this wire a 7 volts, 5 volts, things like that. You need 7 wires to control that work. However, if you use a decoder, it's going to reduce the number of wires you are going to use for the display. And let's take a look at how it's going to work. So the number of inputs depends on the number of digits you want to show to the customers. So for example, I want to show all the numbers from 0 to 7. So there are totally 8 different outputs, right? So we have 8 different output patterns. So that means you need how many bits? 3, right? So for example, we call them as 2, as 1, as 0. And we have A. So let's label all this, give a name to each LED here. A, B, C, D, E, F, G, right? So the middle one is G. We have A, B, C, D, F, G. So all these combinations, okay, these are all these different combinations, and you can assign 0, 0, 0 this input to display a different pattern, for example, 2 or 9. But let's make it easier. So 0, when you have a 0, 0, 0, I'm going to display a 0. So if you look at this one, If I want to display a 0, and you just want to turn off G, but for all the rest of them, you need to give a 1 to keep it to let it up, right? But only G you want to turn it off. So you are not seeing this bar in the middle. If you see the bar in the middle, it's going to be 8, right? So now for 001, I want to display 1. So 1, for example, I want to show these two bars on the right side. So only E and D are being turned on. All the rest of them are zeros. For 2, A and D are off, right? A and D are off. All the rest are on. For this one, 3, A and B are off. All the rest are on. 4 will be this. Okay, so F and BC are off. For this 5, E and B are off. All the rest are on. 6, only E is off. 8, all of them are on. All right, so the decoder will be a chip, will be an IC chip or device, right? So this is a decoder, and you have 3 inputs, as 2, as 1, as 0. So you can see that I'm just using 3 inputs. I can control 7 wires instead of using 7 wires to control 7 outputs. I'm just using 3. So this decoder can reduce the number of inputs being used to make the same purpose. Okay. 1, 2, 3, 4, 5, 6, 7. So A, B, C, D, E, F, G, and every wire of the decoder is controlling one LED. You just connect the output of this one to each of the wire of the display module. So A controls that one, B controls that one, C controls that one, D controls that one, E controls that one. Wait. I made it wrong. Sorry, this is not right. So 1, 2, 3, 4, 5, 6, 7. A is here, B is here, C is here. Get into another trouble. D is here, E is here, F is here, G is in the middle. All right, whatever. This is just letting you know how that works. But you don't need to look at this at all. Right? So now let's design a circuit. So which means every individual output need a logic circuit, right? That's for A. That's for B, right? Etc. It's for G. So you need this, you need this, things like this. So we need to design every individual circuit one by one. So let's look at A. If I only look at A, depending on the input, you want to look at this vertically, and A will be what? So what is A? How do you want to simplify it? So the way to do that is a K-map, right? So S2, S1, S0, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. So look at all these ones. Where do you have 0? Where do you have ones? So 0, 0, 1, you got a 0. 0, 1, 0, you got a 0. 0, 1, 1, you got a 0. So all the rest are ones, right? Only 3 zeros. So now let's loop them, right? So like this, this, and this. It's not really simplifying too much, right? But anyway, yeah, let's assume this is right. If you get a different answer, but you know how that works, so you can derive by yourself. So now let's look at A equals to what? A equals to, so this is A, this is a column for A, so A equals to this two, which is S1 not, S0 not, and this two, which is S2, S1 not, and this two, which is S2, S0 not, and this single one, which is S1, S0. So, and after you know that, so these are the inputs, right? So you know the logic circuit for A will be you know, S1 not, S0 not, S2, S1 not, S2, S0 not, S1, S0. And then OR them together. Okay, so that's the final circuit. That's for A, right? Just do the same thing for B, C, D, E, F, G for all of them. So that's a circuit, and you fit this part into here, right? So that's a part of the circuit of the decoder. That's how you do it. However, think about it. You know, we just have 90 minutes for the exam. I won't let you design all these numbers, right? So for example, I only need to see the customer only say, hey, I just need people to show that number from 5 to 9. No, let's make it fewer. 5 to 7. I only want to show, I only need to show 5 to 7. And how many numbers? 5, 6, 7, right? 3 numbers. So I only have 3 different output patterns. And you only need 2 bits to do this job. All right, let's take a look. So only 3 inputs. 3 inputs, 3 outputs. And if you look at this, 5 to 7. So 5 will be only E and D are off. E and B are off. All the rest of them are ones. For 6, only E is off. For 7, so you only have F, E, D are on. F, E, D are on, but all the rest of them are zeros. Right? That's it. That's a truth table you need for this decoder. And it becomes pretty simple. You don't even need a K-map for this because you have a really limited number of min-terms. For example, this two, you just directly write it down. So for example, A equals to what? A equals to S1 not, S0 not, plus S1 not, S0, right? You can take S1 not out, and which is S1 not. Okay, it's pretty simple. The circuit will be very easy. A will be S1 nut. Okay, just do this pretty simple job for all the other numbers, then you are done for the problem. You need to understand this first before we move forward. Okay. All right. I think I have covered everything possibly will be on the exam. Spend some time. Do not totally rely on the homework assignments. The homework assignments, the problem types in the homework assignments covers about 80% of the exam, but there will be a few other ones. You didn't do it in the homework assignments, but they are in the lecture videos. So nothing will be beyond the lecture videos, homework assignments, and the final review. Okay. Spend some time to work on this. Make probably a checklist. Just check, right? So if you are done with, one of them or all of them, then move forward with another one. That's the way you prepare for the final exam. All right. Here's one thing I forgot to mention, which is, I was thinking about if I should do office hours next week, but I will do it. So if you have any other questions, feel free to shoot me an email so we can make a individual appointment as well instead of in addition to the office hours. I'll always be here to help you guys. All right. Good luck on preparing the final exam.